All right, good afternoon, everyone. Thank you for being here. So, we have a distinguished speaker today. Before I introduce the speaker, I'd just like to say a few words about this lecture series. So, as you know, this is the distinguished lecture series supported by Monty and Pusha Ahuja, who are honored and highly accomplished graduates of Ohio State. They consider their charitable and philanthropic support for the university as an investment for the next generation, that's you, trailblazers in science, technology, engineering, and mathematics. So this series aims to attract highly accomplished and illustrious individuals, such as our speaker today, as well as those on their way to national and international renown. In addition to showcasing the work of experts in science and engineering, we hope to inspire our students to achieve excellence and eminence in their own future careers in government, industry, and academia. So before we start, I'd like to introduce our speaker. You've all read her bio. She's currently a distinguished professor at UCLA, and she's also the dean of the Samuel E. School of Engineering and Applied Science at UCLA. Prior to that, she was a chair of UT Austin, mechanical engineering. Professor Murthy, or Jayati as I call her, is a bit of a trailblazer in many aspects, many respects. She was just 2 out of 200 female engineering graduates, students in her undergraduate class. For those of you women engineers here, you probably know what that means. She's the first woman dean of UCLA, and she was also the second department chair in any engineering department at UT Austin, and the first PhD graduate from mechanical engineering at University of Minnesota. She worked, for those of you who work in the area of CFD, you probably have heard of the simple algorithm and Professor Suhas Patankar. She was his student, and when she finished her PhD, she joined Fluent, which again, most of you know. Fluent was a small startup company in those days, and she was the 6th employee of that company. So the code that you use today, a big part of that is written by her. Of course, all the bugs were introduced later on. So with that, I invite Professor Murthy.
Thank you so much. Can you hear me all right in the back? Thank you so much for having me. I'm really honored to be here. I have many friends in this department. When I was at Purdue, I used to come up here every so often. And so happy to see you all, and happy to see the department doing so phenomenally well. I mean, there's just so much activity going on, so much has changed, the new building and all that good stuff. I really do congratulate you on it. So today what I thought I'd talk about is something that's kind of sort of computational, not entirely heat transfer, but close to it, and hopefully the topic is broad enough that it would be interesting to all of you. The topic of my talk today is automatic code differentiation for fun and profit. And I should tell you right up front that there isn't much profit in it. You really mostly have to do it for the fun. Suddenly keep track of time, please, because I do tend to wander. So I will try and explain some of the basic stuff. It's actually interesting, and we've been playing with it for the last couple of years. All right, so before I start, I should acknowledge my collaborators who've been with me for many years, a couple of my PhD students, Prabhakar Maripalli and Ajay Vadikepar, both of whom are now in industry, and then my longtime collaborator and husband, Sanjay Mathur, who's also a part of this effort. All right, so let's start with what I'm going to be talking about today, and it is really fundamentally the computation of derivatives, which you would think is so trivial a topic as not to actually merit a whole long lecture, but I hope to interest you in why this is actually a fun thing to do. Right? Now, one of the reasons we are interested in derivatives is because we want to compute sensitivities, all right? And sensitivities are just derivatives, adjoints are just derivatives. And so the kind of question we may seek to answer, I'm a CFD person, some of you do other kinds of computations, of course. And so the question we may want to answer is, what input to your computation yields the desired outputs, right? Or more properly, you may want to talk about what we call a tangent problem, where you want to answer the question, how does a specific input affect all outputs of your CFD calculation or something else? And correspondingly, the adjoint problem, where you want to ask the question, how does a specific output, how is it affected by all the inputs into your problem? Right? So you're really looking at sensitivities of your computational code, CFD or otherwise, and you want to answer these kinds of questions. Right? What would you use this kind of analysis for? You might want to determine the effect of uncertainty and tolerances. Let's say that you don't know your inputs sufficiently well. You know them with a certain error bar. One way you could use this kind of analysis is to figure out, if I have this much error in my inputs, how much error do I really have in my outputs? Or correspondingly, if I want to control the error in my output, how much of a control do I need to impose on the uncertainties in my input, right? So that's the kind of analysis you might want to do. Helps you plan experiments better because you know where your biggest sensitivities lie, and therefore you know how to optimize experiments. And indeed, if you're a CFDer like me, the kind of thing that you might want to do is figure out mesh sensitivity, right? That's a kind of sensitivity. Does my drag or lift prediction, how sensitive is it to my mesh? And therefore, what areas of my mesh is my prediction most sensitive to? You may want to have figure out the sensitivity to iteration parameters. I mean, if I said under relaxation coefficients at this or that number, how fast does my solution converge? And therefore, what should they be set at? So many kinds of engineering computations depend on an understanding of sensitivities and adjoints. Right? So that's what we're really talking about today. What is the sensitivity? Right? The most general form, it is really a Jacobian. And oops, I'm sorry, I'm pointer in this thing. I don't know. All right. Oh yeah, here's the pointer. Yeah. All right. So here's the Jacobian. Y is your output, X is your input. Let's say that there are M outputs and N inputs. So your Jacobian is really an M by N matrix. All right. It's just a gradient. You can find Jacobians or sensitivities through a number of different approaches. The most common of which, one way of doing it is a continuous approach. All right? So how do you do this? Let's say that you have a partial differential equation, you've got Navier-Stokes, or you've got a heat transfer equation or whatever. You want to find, for example, you've got your heat conduction equation, right? Laplacian of temperature equal to 0 or something like that. If you want to find the sensitivity of your temperature to something, thermal conductivity or Cp or something else, you could actually differentiate your partial differential equation and therefore derive a sensitivity or an adjoint version of your partial differential equation. So now you've got a different PDE, you can go off and discretize it, you can solve it using your usual techniques, and then that's the way you get yourself a differential equation. Now what's wrong with this? Well, it's nice in many respects, but if you wanted the sensitivity of temperature to specific heat as opposed to thermal conductivity, you'd have to derive a different differential equation, discretize it, solve it, find the answers, etc. So it's kind of time consuming, it's much more complex, you have to write new code every time, you have to derive new equations every time, you've got to derive new boundary conditions every time, etc. Now, we're trying to avoid that. Now, another way of doing this is really a discrete approach. You could try to do this discretely, right? So you discretize your governing equation, your heat transfer equation or whatever, and then work on that discrete PDE to create sensitivities and adjoints, not on the PDE itself, but on the discrete version of it. And I'll show you in a minute that this is actually easier to automate, at least in some respects, right? Okay, so what kinds of things might you use this for? I've used it for a variety of different things. So let's say that you've got a quantity of interest Q, and you've got a specific input variable X. The sensitivity is really the derivative of quantity of interest with respect to X. We use it for a variety of things. Recently I've been working a lot on small-scale heat transfer. I use this kind of idea to find the derivative of the potential energy with respect to the crystal. Depending on the order of the derivative, you can get a variety of different force constants. For those of you who work in phonons and so on, derivative of the phonon frequency with respect to the wave vector gives you group velocities. You can find Gruneisen parameters, all kinds of derivatives reside. I mean, engineering has all kinds of derivatives. This particular case, I'm showing you the phonon dispersion of graphene for those of you who know what that is. And these dispersion curves are derived through an automatic differentiation idea, which I'll talk about in a minute. And gradients of these dispersion curves actually give you the entire set of group velocities, which is very easily done, and I'll show you that in a minute. All right. Now, force constants are not usually just second order. You, depending on the kind of calculation that you're doing, you will need derivatives of higher order, second derivatives of the potential with respect to the atomic position, third derivatives if you really want to be looking at anomalies and so on. And so higher order derivatives are also important. All right. Now, every one of you knows, of course, that derivatives are easily computed, no matter how complex a function you have, using simple finite difference methods, right? So in this particular case, we want the second derivative of the crystal potential with respect to atomic displacements. And second derivatives can be, you can easily derive a second order finite difference formula. This is second order to go ahead and do this, right? And that's certainly one way you can find derivatives. However, what I'm going to talk about is the whole idea of automatic code differentiation. And what this does is it numerically evaluates the derivative of a function, but does it automatically using some of the properties of the C++ compiler. All right. Now, why do I need to go so far? So let's take a look. All right. So what's the idea? What is the idea of code differentiation? You've got a computational code. A computational code is nothing but a series of statements, right? I mean, it's a bunch of algebraic operations working one on top of the other. And what you're trying to do is to figure out the derivative of the output of your CFD computation or whatever else with respect to inputs, right? So let's say that you're doing a heat transfer problem. You've got heat transfer coefficient you're trying to compute, or a temperature field you're trying to compute. And maybe you want to figure out what the sensitivity of that is with respect to thermal conductivity, or C sub P, or geometry, or something else. Right now, your CFD code is really nothing but a set of algebraic statements. Right? I mean, it's just algebraic operations. And the question is, how can I differentiate this code to get the derivative of outputs that your CFD code puts out with respect to the inputs of your CFD code? All right. Okay. So given that a code is simply a set of algebraic operations, let's take a very simple thing here. I've got a variable x, which is a function of an input u, and then there's a concatenation of operations. Y is a function of x in some way, z is a function of y in some way. So you've got a code that's a bunch of algebraic statements. Right? Now, I'm going to differentiate this guy so that x prime is df du prime, and so on all the way down. I haven't told you what prime is. Prime is the differentiation of x with respect to some variable. What variable? Haven't said so yet. That's for you, in fact, to choose. Right? So you want to find dz du. Right? So here's what I'm going to do. I'm going to set u prime equal to 1. Right? What does u prime equal to 1 mean? U prime is the derivative of u with respect to something. So if you choose u prime equal to 1, you are signaling this entire set of calculations to say that prime means differentiation with respect to u, right? Because du, partial u is equal to 1. Partial u means u prime, but prime means derivative with respect to u. All right, that's what we're trying to tell. Right? So if I set q prime equal to 1 in this concatenation of operations, think about what you're going to get, right? So if you follow this through, you will see that in the final step, what you're really getting is easy, right? So keep that idea in mind while we work out a little bit of algebra. Alright, so what we're going to do when we talk about code differentiation is to consider the code as a composition of unary and binary operations. Alright, it's just a series of operations. We know how to propagate inputs to outputs for elementary operations, and we're going to apply a chain rule to actually propagate primes right through the code. So easiest to see while if I were to show you an example. So let's do a numerical example here. And so let's say I've got two functions, P and Q. P and Q are outputs, and P and Q are functions of inputs x and y. Right? Okay. So the first thing I'm going to do is to do a bunch of elemental decompositions. What does that mean? Now let's take the first function. It's got a thing 3x squared. That's a multiplication of 3 and x squared. So the x squared sits in t1, t2 multiplies it by 3, t3 is this guy, t is t2 plus t3. Similarly, q is p divided by y. And so this is breaking down this set of operations into a set of elemental functions. It just multiplies and divides and sine and cosine and so on. Right? Now let's do derivatives, right? So t1 prime is really x times x prime plus x prime times x, right? t2 prime is 3 times t1 prime, etc. You can carry them all the way through. What does prime mean? I haven't told you yet what prime means. Prime means derivative. Derivative with respect to what? Haven't specified yet. All right, we'll do so in a minute. And so let's continue with that. Right. So up top, I've got exactly the slide that I just showed you. This is for your reference. And here's what I'm going to do. All right. I want to find derivatives at a particular point of operation. So at a point x equal to 10, y equal to pi by 3 in this case. And I'm going to do this entire concatenation of operations by setting x prime equal to 1, y prime equal to 0. Right? What does this mean? What does x prime equal to 1 mean? This is a derivative. Remember, x prime is a derivative, right? And if x prime is 1, it denotes a derivative with respect to x, right? dx is 1. Right? So I'm signaling my calculator here to say that I really want a derivative with respect to x. Prime means derivative with x in this case. So if I go through all of this stuff, and wherever it says x and y, I put in 10 and pi by 3. Wherever it says prime, I'm going to put in x prime equal to 1, y prime equal to 0. And I calculate p and q, and p prime and q prime. Look at what you end up with. Right? You end up with a p prime of 60, which you can convince yourself is really partial p, partial x at this point of operation. Right? And if I put in the same thing and figure out q prime, you'll find that the number that you're computing is partial q, partial x at this point in the operation. Right? And you can convince yourself that these numbers are exact to machine precision. These are not finite differences. All you've done is chain rule following through a set of operations. Okay? Now let's do the other thing. Same point, you want to find derivatives at exactly the same point, but this time I'm going to say x prime is equal to 0 and y prime is equal to 1. So what am I signaling my code? I'm signaling my code that I want derivative with respect to y, which is y prime is unit. Alright? And so if I stick this into my entire set of calculations here, sure enough, you're going to end up with p prime equal to 0.5, which you can convince yourself is partial p, partial y at the point of operation. And you can convince yourself that the q prime that you compute is partial q, partial y at the point of operation. Right? So I want you all to stop and think what you're taking away from this, right? Every code is nothing but a series of algebraic operations like this. You already have a code. Fluent computes, fluid mechanics. It computes flow fields, temperatures, etc. It's got a bunch of inputs. And if I were able to propagate, if I were able to tell my code, hey, I want my velocity prime to be unity, and I were able to propagate that prime through my code, I should be able to get derivatives of everything in my code with respect to velocity. Right? So you should be able to differentiate the code in this way. Okay? All right, so let's see how this works. Now remember that the derivatives are exact. I'm not doing finite differences. These are exact to machine precision. You can convince yourself of that. I'm not doing symbolic calculations. This is not any kind of symbolic calc. This is a numerical calculation that's just been passed through this code. And so I want to make the following points, right? Exact derivative with respect to the variable for which you set the prime to unity. This is not a finite difference approximation. I'm not doing delta f by delta x or any of that stuff. Now each variable and its prime must be stored. So if you want your code to be differentiable, you have to be able to store the value and its derivative, whatever order of derivatives you want. What you're getting is the numerical value of the derivative at the input condition. This is not a symbolic differentiation. And I'll show you in a minute that this all works through loops and conditions and iteration. It can work right across any code that you have. All right. Now the question is, how do you implement this in a code? What I'd like to do is to differentiate any code that you have. I've got a Fluent, I've got a MATLAB, I've got a finite element code. I want to be able to differentiate the code. What does that mean? That means I want to be able to get derivatives of anything in that code with respect to inputs that I would choose at the time I want to run the code. I want to do this unintrusively. I do not want to go into Fluent and write every 1 million line of code in Fluent. I have the variable and I've got an expression for its prime, and I don't want to go change the code at all. I want this to be utterly unintrusive. By hitting a button, I want to be able to get derivatives. All right. So how do I do that? Now, you cannot do it for if you've got a code written in 470 or something, you can't do it. But in any modern code, you should be able to do this pretty much automatically using two different ideas. The first of these ideas is templating. Right? Now, I want, in the case that I've shown you, to be able to carry not just the regular variable, but its prime or derivative. And so I want two things to be carried. Right? Every variable should really have a value itself and its derivative. You as a user will tell it what the meaning of the derivative is. Is this a derivative with respect to velocity, temperature? That's for you to choose at runtime. Right? So every variable in this case is two things. And so I want to, so that idea is called templating, right? So just as a typical computer language will allow you to declare variables to be double, precision, or float, or whatever, you can, this is essentially a user-defined variable. And you can define that variable to be two things, a value and its prime. You can do other things too with the templating idea, but in this case, let's say we're going to say this is going to be a value and its prime. The other thing that I'm going to do is operator overloading. So what I'm going to do is redefine what plus, minus, divide, multiply, and other operators are. All right. So for example, a typical multiplication operator will take the two variables and multiply them together. But I want to change, or I want to overload the meaning of the multiplication operator. So when the multiplication operator works on this variable, which has got two things in it rather than just one, the first variable, the multiplication operator does the usual thing of multiplying stuff, right? However, when it works on the second variable, the multiplication operator essentially plays out the chain rule. So instead of just doing multiply, it'll do uv prime plus vu prime, right? So I'm changing the meaning of multiply. And I can do that for all other things. I can do sines and cosines, I can do exponentials, I can do divisions, whatever. I can overload the meaning of arithmetic, of operations so that they work meaningfully on not just the variable itself, but also its prime. Right? Now you can see how powerful an idea this is, because if I can change the meaning of the variable and I can change the meaning of operations, I can easily convert an existing code into one that does the regular calculation and also does derivative calculations automatically. Right? And so here we go. So let the compiler do it, all right? So let's say that you've got a simple original C++ code with exactly the algebra that we were talking about now. These things have all been declared to be double x and y, double p and q, and it's doing the thing that you want to do. How would you convert this into a code that does automatic code differentiation? You can do this. First of all, you define a new template, a new class, all right, t. And this t really contains two things, all right? So it contains, so t contains, so if, x and y used to be just regular doubles here, but now you declare a new class, and that contains x and x prime, all right? So whenever you've got an x, it's really carrying two things. And we're going to overload all operators, all these multiplies and signs and divides and all of these will be overloaded. And if you do that, this piece of code, which really looks pretty much like the other guy, other than that the variables have been redefined and the operators have been overloaded, nothing particularly different about this chunk of code versus this chunk of code. It looks nearly the same. All right, all you got to do is change the headers. And if you do that much, you have this powerful tool that converts your regular code into one that not only does the forward calculations of temperatures or velocities or whatever, but allows you to do derivatives as well with respect to variables that you would define in your input stack. So when you're putting in inputs, you would say, give me the value of derivative at a particular value of x, and if you said x prime equal to 1, it understands that the derivatives will be with respect to x. Right? So it makes it very, very powerful. Alright, so you can do this for other things too. We've been using it for second, third order derivatives in nanoscale heat transfer, in fluid mechanics, etc., etc. And so that's basically the idea, is you're propagating derivatives from inputs to outputs. Alright, so let's take a look at what we can use this for. Now, one of the first things we do is to try and benchmark it against finite difference calculations. In this particular case, this is actually potential energy with respect to a graphene nanoribbon, actually. Or rather, no, this is bulk graphene, a test of potential for bulk graphene. And what we're doing is we're trying to find the derivative of the potential energy of the graphene with respect to a change in one of the atom's positions. And one way to calculate it is through a simple central difference, finite difference idea. And the red is really that guy. Right? The blue is a code differentiation idea. You have a function which has the potential energy of graphene, and you're finding its derivative with respect to the atomic position. Notice something. Now the x-axis is really the delta x in your finite difference calculation. Right? Now you know that finite difference accuracy depends on the delta x that you put into your derivative, right? And so as you decrease delta x, the finite difference code becomes more and more accurate, and in fact approaches the code differentiation value, which is independent. It has no idea of delta x. We don't do it through finite differences, and so the two actually converge to the same answer. But of course, the code differentiation gives you the exact answer the first time you try it. You don't have to be doing, figuring out what delta x is good enough, right? Now, if you look at other derivatives, this is a second derivative. Again, code differentiation always gives you the right answer. Finite differences require you to keep decreasing delta x to get to the right answer. But you get anomalous behavior as delta x tends to 0 because your computers are finite word length and things can blow up if you're not careful. In fact, you see that really dramatically here. This is third derivatives of the potential. Code differentiation gives you the exact answer every time. Finite differences require you to decrease delta x till you get independence. But if you get too small, you get all kinds of craziness near delta x equal to 0 because you're dividing by 0. Right? So you've got to be careful. So code differentiation is independent of delta x and will give you the right answer every time. Other things, let me quickly run over this. This is phonon dispersion of graphene. You don't need to know the detail. We're finding force constants using the Tirsov potential for those of you who play in the space. The function whose derivatives we're trying to find are very, very complex. And we find these derivatives through automatic code differentiation. And so let me show you what we get. So phonon dispersion this is phonon dispersion computed using force constants using code differentiation, and we get very good answers. And from these from the dispersion curve, we can find group velocities, and these group velocities are really derivatives of the crystal frequency with respect to the wave vector, and that's how these are found. Now, if you go off and find them, the one thing I do want to say, for those of you who play here, group velocities are exact, and they don't run into many of the issues that people run into trying to resolve phonon polarization branches. Right? So, and if you look at force constants that we actually get using this kind of method, they satisfy symmetries and things that are otherwise hard to obtain. All right, so here are phonon group velocities. Finite difference methods, code differentiation all give you the same answer. It's just that code differentiation is very, very easy to do in this case. Here's a calculation of Gruneisen parameter. Again, a parameter associated with, in this particular case, we're finding it for nanoribbon graphene. And if you look at code differentiation, very, very stable, does a great job. If you look at finite difference methods, they can all go crazy in certain regions of the dispersion of the gamma m direction, only because finite difference derivative, you have to be very careful about them. All right, here's another one. This is the temperature sensitivity of specific heat of a crystal. So what we're doing is we've got specific heat of crystal. We want to find its temperature derivative. You can do it by hand, but complicated. Automatic code differentiation gives you these answers instantaneously, and all of these power laws are, in fact, you can show that they're absolutely exact. Right? So that's the whole idea here. Let me give you another example. This is out of computation fluid dynamics. Right? So gas turbine cooling example. So let's say that you've got a hot surface. This is the outer surface of your gas turbine blade. Interior to the gas turbine, there's a coolant running. That coolant is pumped out to the surface in order to cool it. Outside are the hot gases, basically. And that's what you're trying to protect this surface from. And the coolant is supposed to be injected and flow over the turbine surface to protect it from the hot flow. Right? Very classic CFD problem. Lots of folks have cranked velocity fields and temperature fields and things like that here. And so what we'd like to do is to compute the sensitivity of the flow and temperature field, not a particular value, but of the entire field to hot gas inlet velocity. So the question I'm asking is, how does the field change if I change the input temperature or velocity or whatever else? So here's the answer. So here, there are some parameters in the problem, don't worry about them. What I'm showing you here is the u velocity field in this particular instant. You've got flow coming in here, you've got coolant flow coming in here, the two mix together. This is my velocity field, this is the u component of the velocity field. Right? That's just your regular CFD calculation. Now what I'd like to do is to figure out the sensitivity of the u velocity field to the inlet velocity. How does this guy change if I change that guy? Right? And so this is a field calculation of the derivative. This is a derivative of u with respect to the main field velocity. And it tells you something that's actually kind of obvious. The velocity field in the main domain is very sensitive to the inlet. Now, the coolant flow, of course, is insulated from the main flow, and in fact, it has very little sensitivity, right? And that's kind of perspective. So you can find derivatives of entire fields with respect to other variables. You can find derivatives of singular quantities with respect to variables. And so very, very powerful idea. Here's another area in which we've been using the same kind of thing. This is topology optimization, which some of you may be playing with, all right? So what is topology optimization? Let's consider this problem, right? So you've got a square domain, insulated on all sides. Sitting inside is some kind of a mixture of two materials, right? Material 1, which is high conducting, material 2, which is low conducting. You've got, in this particular case, 40% of high conducting material by volume. Inside it is also a volumetric heat source. And the question we're asking is, what kind of physical structure consisting of material 1 should be constructed so as to minimize the mean temperature? So I'm not telling you what the shape should be. I'm saying, go figure out a shape for me that would minimize the mean temperature. Right? So optimize a topology form. So I'm not telling you, here's an airfoil shape, tell me what its chord length should be, etc. I'm saying, go find me a shape that minimizes. Right? So typically, topology optimization, what we do is this. We determine the distribution of the material to minimize some kind of a cost function subject to constraints, which are really the partial differential equation with boundary conditions and the fact that you've got a certain specified volume, and there may be other constraints. Alright, so how do you do this? In this particular case, what we do is we've got a computational domain. I'm going to break it up into elements of finite volumes, and I place material 2, which is red, in a background of material 1. Material 1, which is red, in a background of material 2, which is blue. And I'm going to move these pixels around while minimizing the cost function. Right? Just a good old optimization problem. And if you go off and do that, you can come up with structures which are optimal for certain ranges of thermal conductivity. Right? Now, the way this is done is really through gradient descent kind of ideas. And gradient descent ideas require gradients, and gradients require essentially sensitivities, and we do that through automatic codification. Right? So that's the machinery that sits behind this whole topology optimization idea, and it's one big use of sensitivity calculation as well. Right, now the last problem I want to throw at you. How are we doing for time? Okay, not too bad, getting there. Alright, so this is a little more complicated, and this works off some of the work we were doing with respect to making probabilistic computation. Alright, so what do I mean by that? Let's say that you're doing a very simple heat transfer problem. Del dot of K grad T equal to 0, good old heat conduction equation, but with a little twist on it. So what we're going to say here is that the thermal conductivity is not a known constant, but is in fact a distribution. All right? It is normally distributed, let's say, about the mean, and you know what the standard deviation of your thermal conductivity is. So you're not sure what the thermal conductivity is, you think it is distributed in a certain way. And the question I'm asking you is, if you know the distribution of your thermal conductivity, let's say that it's normally distributed, what is the distribution of the temperature as a result, right? So you have a calculation domain. Rather than having a temperature at every grid point in that domain, I've got a PDF of temperature at every grid point in the domain. And that PDF of temperature is caused by the fact that your thermal conductivity is not a single number, but is now a distribution. You don't know what the exact number is, you think it's a distribution of something. So you're trying to make probabilistic predictions of temperature rather than deterministic predictions of temperature. All right, that's the problem I'm trying to solve. If you have uncertainty in your thermal conductivity, what is the uncertainty in your temperature? Now, this problem is not new. There's a vague literature on it, and one of the ways you deal with it is something called generalized polynomial chaos, GPC. And what is the idea of generalized polynomial chaos? Basically, what you do is you've got your probabilistic variable k, which is the function of, in this particular case, a linear function of a random variable epsilon. That's why it's probabilistic, and epsilon's got this distribution. And the way we represent this guy is through a polynomial basis. We expand k in terms of a coefficient, which is a function of space, and a polynomial, right, which is a function of random variable which has a distribution. Right? And so this is how the input is represented, and we represent the output in the same way, which is that it is also a summation, a series sum of a coefficient and a polynomial. And you can choose the degree of this expansion depending on how well you want to represent how far you want to go in terms of representing the randomness. So the way people do generalized polynomial chaos is that you take these expressions, you stick them into a governing equation, you perform a Gallatin projection to separate out these PDEs, and what you end up with is a separate PDE for each one of these coefficients. You discretize the PDEs, you solve the polynomial expansion to find these coefficients, and then put the thing back together to get your probabilistic expansion. That's the way generalized polynomial chaos is done. Now we decided to do this using our operator overloading idea, because what we have here is horrible. It means you've got to derive new PDEs for coefficients, you've got to have new solution methods for these crazy PDEs that you get for these coefficients. Every time you want to change a variable that's random, you've got to do a new code, all of which is not what we want. And so look what we did, all right? We're using the same idea of templating and operator overloading to actually make a deterministic code into a probabilistic code. How do we do it? Let's say that you've got all the variables in your code. I'm going to expand them out in these polynomial expansions, all right? And now each variable is templated as being of the polynomial chaos class, right? Which means what? Every variable now carries a bunch of coefficients. Not just one variable, it carries all of its coefficients to whatever level you want to expand this. And when you multiply coefficients, so C equal to A times B, for example, I'm going to do overloading, but now the overloading is really quite elaborate, right? So what I'm trying to do is multiply. When I multiply two variables of this kind, it's a multiplication of two series, the performance of a Gallatin projection, and the isolation of the value that you're trying, all the coefficient values that you've got. So you can make this extremely complicated, all right? So you've seen how operator overloading allows you to do derivatives. Man, you can do a whole lot of operations hiding under the multiplication operator that does Gallatin projections and isolation coefficients, etc. You can do a lot of stuff hidden under these operations. And similarly, for multiplication, division, whatever, Sandia has a UQ toolkit that in fact allows you to do this kind of overloading really easily, and that's essentially what we did. And so your code can look exactly like a deterministic CFD solver, but sitting underneath is this whole undergirding that allows you to convert a deterministic solver into one that actually does a probabilistic prediction. Right? So let me give you an example. Right? So no need to recode everything. Your code looks exactly like it did before. All you got to do, no need to do everything over and over again. You add a model, it's all in the code. If your code does it, you can find a polynomial version of it. Nothing needs to be done. Right? So easy to put together. So let me give you an example. This is your CFD practitioner's dream problem, the driven cavity problem. Right? So you've got a cavity filled with fluid. 3 of the walls of the cavity are stationary. The upper cavity moves, in this case, to my left, and drives the fluid inside, and the fluid goes round and round in circles, and you can compute the velocity fields, etc. from it. And let me put a little kicker on this problem. I want to figure out, I want to do a probabilistic computation, and the probabilisticness is caused by the fact that the viscosity is not a given number. It is in fact a distribution. In this particular case, it is a Gaussian distribution with a mean value of 1, standard deviation of 0.1. All right, so I'm just sort of telling you that this is what the viscosity is. And the question I'm asking you is, tell me what the distribution of the velocity field is. What is the PDF of the velocity field that results from this PDF in the viscosity? So at every point in the domain, I have not just a velocity vector, but a distribution of the velocity vector. Right? So that's what I'm trying to find. Some details here, not terribly important, so let's move on. Right, so here are the kind of predictions I can do with this kind of idea. Right? So what I'm going to do is plot on the vertical center plane the velocity of, I'm plotting the u velocity I'm not just plotting the u velocity, I'm plotting the mean of the distribution that I just predicted, and this is what the distribution looks like, right? I'm comparing that with Monte Carlo sampling, so I sample my viscosity, I do a 500 calculations, and I plot that, and they all fall one on top of the other. I'm also plotting here the standard deviation of the velocity, because I'm not just computing the velocity, right? I'm computing the entire distribution. And again, the blue is our polynomial chaos computation, and then there are other things to compare with, Monte Carlo simulations. Turns out actually our polynomial chaos is very accurate. But the main thing I want you to take away from this is that we are now computing not just the velocity field, but the entire distribution of the velocity field at every single physical point in the domain. Right? More of the same is v velocity distribution, the mean, and the standard deviation. Right? How has this been done? You've got a standard CFD code. All I've done is just overload the heck out of these operators, do all of the polynomial chaos computation sitting underneath, and you can convert a deterministic code to a probabilistic one. Alright, so let me close here by saying this, alright? I know derivatives are simple, stupid things that you learn as, in 8th grade or whatever, but finding derivatives of complex codes and complex operations is of high interest. Doing them automatically is of high interest. Doing them unobtrusively is of high interest. I never want to be coding stuff. I don't want to be writing lines of code for derivatives when I've got lines of code for the function itself. And I've shown you here an idea of how you can do it automatically without ever mucking around with your code, right? You can use this to do many things. We are playing around with it to do quantum calculations now with quantum espresso. Can be done for other kinds of variables. You can compute Jacobians, you can compute Hessians, derivatives of higher order. And as long as you've got a code that allows templating and operator overloading, C++ does it, modern versions of Fortran do it, you can actually do a lot with almost any code that you've got. Right? So let me stop here and take questions. Yeah, hi.
Very interesting. I'm hoping some of the students go into CFD after listening to this. The question I had was, in your example of the cavity, you varied the viscosity.
Yeah.
Right? So when you do that, you're varying Reynolds number for practical.
Yeah, yeah.
If, say, the cavity flow goes to a bifurcation,
yeah.
Is there any way this method will say, this may be that something that the user should, in fact, look at more carefully?
That's an interesting thing, because that should show up in the calculation, at least in terms of the PDF. I mean, that should show up automatically. Right? So there'll be, let me take that back. It depends, right? A bifurcation is a sort of a discontinuity. So the question is whether the polynomial chaos expansion in the random variable is actually able to pick up a discontinuity. These are polynomial expansions. So that's a good question. I hadn't realized how good it was till I started answering it. I think that's the catch, is whether a polynomial expansion like this can actually catch discontinuities in behavior with respect to the random variable. That's where it may fail. Right? If it's an actual bifurcation, it may not be able to catch it. Yeah.
So analytical example that you showed, they had supposed differentiation.
Only in the sense of the chain rule, and that's
Chain,
it.
yeah. So it's how do you implement the chain rule that you report?
That's through operator overloading, right? So you
So
overload.
you need to really your program language, or I don't really know that 60 class.
Yeah, but I mean, if you had 490 or 95, all of them allow you to overload operators. So I need to do this. Hang on, let me find you the slide.
I think it was 30.
Yeah, hang on, let me see if I can. Yeah, here we go. So this is the key to it, right? So two things you need. You need to be able to define variables that are not just the thing, but it's prime. So every variable in your code, your compiler has to understand that this guy now is not just one thing, it's really two things, right? That's the first thing. The second thing is that the compiler has to understand that star now no longer just means star. It means star if you're talking about the first part of your composite variable, but star means entirely something else when it's working on the second part of your variable. And what star means is, when you do a star of two variables, the second guy gets operated on exactly like it's a chain. That's the way it understands it. Okay? So there's nothing symbolic beyond this. All you're telling your code is, now if you have a cosine function, if it's operating on the first guy, it does a regular cosine. If it's operating on the second guy, it really does sine x prime. So you're changing the meaning of what the star operation means, all right? And you do have to define it for all the functions that you have in code. If you have sines, cosines, divide, multiply, exponential, you'll have a header file that actually contains the definition of what these functions actually mean. Right? That's the way the code knows to do what it does.
So, when it's called, when the function is called, exactly which one is the code for the
If you compile the operator overloaded version, it will compile both. It will do both. And so the inputs to your problem would be, you decide that u prime is equal to 1, so you want derivatives with respect to u. You would put that into your input. You're using the operator overloaded and templated version of your code. So once you run that version, you get both the value and its prime. Yeah.
And this is just encoding the chain rule. You alluded to that you've got to have, seems like, some sort of a lookup table for every function that is going to be used here to be able to find this derivative.
Yeah.
So you're saying there's no symbolic math going on.
Yeah.
That lookup table is your symbolic math.
So I don't know what you mean by lookup table. The operator overloading is what you're calling the lookup table.
Overloading is not the issue at all. I'm talking about saying that if you have cosine, then the derivative is minus sine. If you have tan, the derivative is this. That's the lookup I'm talking about.
Yeah. That's your header files would have that.
So you've got to have all of that. And when you have complex expressions, I don't know how you take care of all of these possibilities.
No. What complex expressions though? Give me an example.
Square root of 1 plus cosine squared something,
Yeah. So so it's.
You're going to break up that whole expression?
No. All I need to do is define what the operator overloading is for a square root, for cosine, for algebra, for all these functions. I don't have to do a different one for every kind of expression that you might write. Only the fundamental operations. Right? I don't need to say, okay, today you want square root of this plus cosine of that plus the tan something else. I don't have to write a special piece of code for that. I do need to tell my code how to differentiate square root, how to differentiate tan, sines, cosines, whatever. Right? Whatever functions that you would use would need to be defined. You can use them in any combination you want. I don't really care about that.
Other questions?
Thank you for the amazing presentation. So I have questions on similar lines what Professor asked. So one is that you define all the your symbolic differentiations in the overloading. So how would this method compare to, say, a simple computing the Jacobian using the symbolic toolbox?
Yeah.
How would it compare in that sense? And in terms of time of computation. And second question is are there some cases in which we might not be able to do a symbolic computation and we'll have to refer to some sort of the automatic overloading that this was?
Okay, I confess to never having compared symbolic computation to this. This of course gives you no symbolic answer. I mean, there is nothing symbolic that comes from this. This is purely numerical. And the cost in this particular example is something like 1.5x or something like that of the straightforward calculation. So these are very different things. I mean, I don't even know how to compare them. Symbolics actually give you an expression, and so it gives you a symbolic idea of the answer. So it has its own deep value. I wouldn't, necessarily take away from that. This gives you numbers, right? It gives you no theoretical idea of the thing that you're getting. So if you say, okay, I want the derivative of a cosine function and it's a sine, in your mind you know that that has a certain understanding and a certain value of what cosines are versus exponentials are. This has no such understanding. It's giving you numbers, and that's all it's giving you.
Because what I believe is when we look into the code of the symbolic say differentiator,
Yeah.
it will have this lookup table of all the differentiation methods. Like that.
Yeah, but this does, there's a big difference. The difference is that this is defining a rule for operation, but that's it. I mean, it's not giving you any kind of expression, right? It doesn't know that.
Yeah, but like if you were to code a symbolic operator by yourself, then you'll have a lookup table in this case, and then you'll be using that lookup table to compute your differentiation.
Yeah.
So it's essentially the same process, and you can do the, like you said, you're using the z dash. You can assign it whatever input you want to be. You can choose that for that also, like say Jacobian of f versus b or x or whatever.
Right, yeah. But the difference again is we're carrying no symbolism here. There's no at the end of the day, you will not get an answer in sine or cosine. You will get a number, and that's all it is.
Any other questions? I'm guessing the difference between the two appears when the derivative is very expensive. Then this overloading becomes very derivative.
I mean, that's an interesting point, right? I got to go see what. I mean, symbolic gives you so much more than a pure number, right? So it's more than, I mean, there may be a cost advantage, but a symbolic differentiation gives you an intellectual idea of the answer, which this doesn't. This gives you numbers. There's a big difference.
I'm not sure I understand how the error computes. So suppose I have an inherent error in my numerical solution.
Yeah.
And then I'm calculating derivatives. Say with respect to a particular prime number. How do I quantify that error?
The error of what kind? Round off, or what kind of error are we talking about?
Oh, because if there's an inherent uncertainty in the solution that I just got that I'm
Two different things, right? So it's really important to differentiate what kind of errors you're really talking about. Right now, any calculation that you do on a computer because of finite word length has errors, and this also will have exactly that kind of error. So if you have a certain amount of word length, then you have precision only up to a certain point, and all derivatives computed this way have the same error as your primary computation, nothing different. Because all you're doing is, you're doing just a bunch of extra algebra, and that's the same thing. Right? So none of that changes. Now, error of the type you might have through a finite difference expression or something is numerical error, which this has nothing to do with. It never touches any of that. So yes, so this has the same arithmetic error that you get from finite word length. Nothing else.
So I had a philosophical follow-up question with respect to what we were just talking about. So the way I understand it is that U and V are things that you are sort of computing anyway, and time you want to calculate difference with respect to them, and you do that by an algebraic manipulation of what U and V is. So whatever error exists in U and V because of the way you're computing it, which would also entail finite difference type errors, would also exist in something like Z prime that came out. So that's where I can't understand how the graph for Z prime is a complete horizontal line, completely oblivious.
That's because you're not using this idea at all. Okay, so here's the thing. Yeah, you're talking about this. You're saying, why is this guy flat?
Yeah.
Because I am not using a finite difference. There is no delta x in my operator overloading idea. The finite difference, what does it do? It finds u at a particular value of x plus delta x, finds u at x minus delta x, divided by delta x. You have to tell a finite difference expression what delta x is. And as you make delta x smaller and smaller, you will get the right answer, right? You know that. Code differentiation has no concept of delta x. There is no, you are differentiating the code through a chain rule. You're never using a finite difference idea at all. So this guy is always, it doesn't know anything about delta x. You're not even using that idea.
I mean, it doesn't know anything about delta x directly, but then the things that it's using to compute those multiplications and divisions that goes in on the inside, those things know what delta x is.
No,
and
there
those
is no concept of delta x at all. I mean, you're not taking function at this point and function at this point and dividing by delta x. It is being done through propagating chain rule derivatives, which have no delta x.
Could you shed some light on the runtimes for these codes?
Runtimes, yeah.
At least this overloading, do they take longer time, or how does it compare with
The upper limit is something like 2x, typically 1.5x. X is for the simpler problems, right? To some degree it's problem dependent.
So it would depend on the overloading operator.
Yeah, it depends on how many operations are done here. Yeah, I mean, like the polynomial chaos one is very expensive
right,
because
yes.
I've got the heck overloaded. All of that,
Really good talk, actually. My first question would be, how do you tell the code to recognize which Z prime templating parameter to use? Like, if suppose we do not know the interaction of U and V variables and its entire effect on the Z variable, the output, how do you tell if the code should take Z prime as U into V or U by V? Like, how do you tell that?
No, that's up to you, all right? Z is a function that you define. Right? You decide, I'm going to figure out the heat transfer coefficient or something else. So Z is the thing that you are trying to compute. You already know its dependence on inputs. You're writing the CFD code, right? So you're solving Navier-Stokes, and so you know how the velocity field depends on viscosity. You've got a code written, or you've got a function written. So the function definition is yours. I mean, you have a function you want to differentiate. All right, so you already know the connection between Z and U and V. That's up to you to define, right?
So, how would it know in a black box system where we do not know how the input functions are affecting the output functions, or which input functions are affecting the output functions?
Yeah, so there's something sitting in the black box, right?
Yeah.
Right? Somebody wrote a code, even if you did not write it, it sits in that code, right? Now, that code is, the compiler knows what that code is. It's not a secret, right? I mean, it's a black box to you, but the computational engine knows what it is. I mean, there is a code that's been written, and therefore the relationship between input and output is encoded in the solver, right? In the software that you already have.
So, does this code compute Z prime, like all kinds of Z prime?
Yeah, it can compute, whatever. Look, you've got a number of outputs in your code, right? Or you have many different steps in your code. Each one of those is a variable whose prime you would compute, right? So it computes all of those as it goes through the code.
I think I'm not able to explain my question.
Okay.
So, if it is like a black box system where you do not know the interaction of, or essentially what are the input variables that is affecting the output, then how does the code know which Z prime value to take into account to compile the final result, or does the code compute all the Z prime values
Computes all
and
the
then
Z prime.
calculates the error?
Yeah, that's right.
Okay.
Yeah, it does all of them. Yeah.
So my next question would be, how is this technique different from right now the statistical machine learning techniques?
Oh, this has nothing to do with machine learning. Though many machine learning techniques do use automatic code differentiation for some of the gradient descent kinds of problems, but that's just the engine. It has nothing to do with machine learning. Entirely separate.
Because in machine learning, the weights of the input parameters are they're also calculated using the Jacobian matrix.
Yeah, right. So Jacobians are used in all kinds of things, right? So I guess what I'm trying to say is that the calculation of neural net weights, for example, do use things like gradient descent kinds of methods, and gradient descent kinds of methods typically do need derivatives because you're finding gradients, and gradients can be found through automatic code differentiation. And in fact, you know, if you look at TensorFlow or anything else, a lot of them have automatic code differentiation machinery in them to allow them to do that. But the idea of machine learning has not directly got to do with this. This kind of machinery can be used to drive the engines that drive machine learning codes.
In the case of a total chaos example, you say it takes much longer to compute because the operator overload is much more complex.
Yeah.
But the answer that you will typically get is to do Monte Carlo, so it would be That would be like 500, whatever.
Yeah.
So in some sense you get,
Yeah, so that's a very good question, is why polynomial chaos, why don't I just go to Monte Carlo? Of course, the crossover point depends on the number of random variables, etc. And that's a fair point.
Okay, I think in the interest of time, we'll close. Let's thank our speaker. I want to remind everyone that there is a reception upstairs, so feel free to join and ask more questions.
Thank you so much.
Just a moment, we have a little token for Professor Mukti. So we have a plaque here which says, so this is the plaque given to her for this talk. It says for showcasing eminent research and inspiring future leaders, Monty Arusha Ahuja Distinguished Lecture Series, November 22nd, 2019, Professor Day.